Hybridization. Hybridization in the chemistry world or the chemical world or the atomic world is really just like hybrids that you'll find in nature. It's just a mixture. So we know some very popular hybrids. The mule is a horse and a donkey. A jagulon is actually a hybrid of a jaguar and a lion. A liger is a male lion and a female tiger. Tigon is a male tiger and a female lion, and a zonkey, a zebra, and a donkey. More hybrids that you might be familiar with. A Meyer lemon is a hybrid, a mix between a orange and a lemon, and of course our very popular now hybrid car is a gas and electric run vehicle. Well, what about in chemistry? Well, it's the same sort of thing. Hybridization is when two or more pure atomic orbitals, S, P, and D, can be mixed to form two or more new hybrid atomic orbitals that are identical and conform to known shapes of the molecules. What can get hybridized? Well, all single bonds and all lone electron pairs. Just some quick definitions here. You'll see a sigma bond, and that is just a bond between an s and p orbital. Each is a bond between s orbitals or an s orbital and another orbital, such as a p orbital. So you might have two s orbitals, sigma bond, or s and p, which is also a sigma bond. So that's an sp, sp2, or sp3. Pi bond is when you have two p orbitals sharing electrons in a covalent bond. So that would be two p orbitals in a hybrid scheme. That would be a pi bond. Let's look at an analogy of hybridization. Say there's some dreamy high school boys here at the table. They're over at Chuck E. Cheese, you know, the usual cool teen hangout. There's two here at this table, and there's one here, and one here over at this table. Just kind of chilling around, acting cool. They got their cool top hats on, and as most high school boys are, they're looking to meet some nice young ladies. And in fact, Chuck E. Cheese is a cool hangout place, and there we have some nice young ladies there. So hey, look, there's dreamy U of D boys or Brother Rice boys at that table over there. Let's go over there. The saunter over there, and well, there's no room at this table, so there's hey, look at me. Oh, hi, how you doing? Well, hello. Well, these two kind of are stuck here. These are stuck by themselves, and these are stuck by themselves. So the only ones who get to actually meet are these guys. So we really got to help these people out, and they are not very happy. There's only two groups that are happy, and Chucky sees that. And Chucky says, hey, you know what? I don't like anyone at my pizza place being unhappy. Why don't you guys hybridize your tables, and then you'll see everyone will have a great time. Okay, let's hybridize. So everyone just leave the place they're at, and let's move these tables together. We had a situation like this, and now they're going to move everything together. We have 1, 2, 3, 4 spaces. We combine it, and the high school boys will split up now. All right, now they each have room for a fellow lady friend. And the lady friends will come and sit by them. And now we see that they are all sharing their tables. Everything is shared equally. Everybody's happy. One big happy family. They can all enjoy their pizza. So we see that Chucky gives them the thumbs up because they hybridized. Their sharing is much more equal. Everyone's happy. It's all good. Let's look at an example where hopefully this will make more sense. If we take an element silicon tetrabromide, we see that silicon has 4 bonds with 4 bromine atoms. Now it's supposed to be bonded equally. And okay, yeah, that makes sense. Silicon needs to get 4. Bromine just needs 1 bond. But if we look at the orbitals, Let's look at silicon here. Now silicon, we'll just look at the 3s with 1, and then we have a 3p. So silicon has 1 electron there, 1 electron there, another electron, and another electron. Well, if they're supposed to share 4 bonds with the bromine equally, where will it go? Where are those bromine electrons going to go? Here, here too, and they're not sharing there. They are not sharing. They just happen, these electrons just happen to go into this orbital, but that is not sharing equally like the bromine would do in this case. So for a silicon to accommodate the bromine electrons, it's going to have to change the shape. It's going to have to hybridize. We want a equal sharing. So let's look at a hybridization, what goes on there. How hybridization is going to work is we're going to get the S is going to move up, the P's will move down. So we hybridize the S and the P, and then the electron will move. Now watch here, we have the 3s electrons. We have one will go here, and the other one will go here. Then from the P, we have those electrons will spread out. Now look at this. Now we have room in each of these orbitals to share an electron. So what happens is we have the bromine atoms now come in, and they share those electrons. There's equal bonding between it. Here we have the sp3 orbital. The black electrons come from the silicon, and the red would be from the bromine. So the S and the P's combine, they hybridize to form their own electron levels. sp3 hybridization. We had 4 bromines, which were responsible for these red electrons. The silicon had the black electrons. Now what about an sp2 bond? If we look at boron trifluoride will have 3 fluorine atoms coming off of the central boron atom, and they're each at 120 degrees, each going to be shared equally, farthest apart as they could be. We need to understand that those electrons and everything must be shared equally. Look at the electron configuration of boron, the central atom boron. We have the 1s there, and then the 2s, and then there's 1, 2p. Well, you're not going to get equal sharing if you're just going to have this. So we need hybridization. We need for that S and the P to combine. S coming up, and the P's come down. Now those atoms for boron, the 2 electrons from the s orbitals will spread out, and then we'll have the 1 electron from the P coming down. Now this leaves perfect bonding opportunities for 3 electrons from each of the fluorine atoms. We get 1 fluorine coming here, 1 fluorine coming here, and 1 fluorine electron there. And now we have an sp2 orbital, or hybridization. This came from the S, and this was from a P, and this is from a P, so that's why it's sp2, 2 P's. What about an sp or sp1 hybrid orbital? Beryllium fluoride. The beryllium fluoride, we have the central atom beryllium and then fluorine, and that's 180 degrees here. We have to have equal sharing. The only way we can do that is if we have a hybrid orbital. So if we look at the central atom beryllium has an electron configuration of this, but we have to think of where are those fluorines going to go? I mean, how are they not just going to be stuck in here? They're not just going to be doing that. They're actually going to have to share an electron. They're going to have to share an orbital. It goes into hybridization mode. S and a P, we'll put 1 orbital down there, 1 electron there, and another there. That is from the beryllium atom. fluorines have a perfect opportunity to match up here, and now we have an sp hybrid orbital. Now you might think, well, hold up, fluorine's happy. It just has that one electron it's bonded to. That's all it needed for the octet. Beryllium, though, how come beryllium doesn't have a full octet? It doesn't have 8 electrons. It only has 4. Well, the thing is, there are exceptions. They're not always going to have a full octet. The octet rule is a general rule. There are going to be exceptions, and this you might think as well would be ionic bond, but in this case it is a covalent bond. Not all atoms or compounds are going to have each element with a full octet.